LIC. Let's watch a video on LIC.
Hey everyone, welcome back to Take It Forward. Today we will be starting with another pattern of DP, which is the LIS pattern, or the longest increasing subsequence pattern. Now we have done some problems on subsequence. If you remember well enough, the DP 13 to DP 22 was based on continuous. Like you can pick up 10, you can pick up 2, then you can pick up 5, then you can pick up 7, then you can pick up 101. So if
Oh, yeah. Yes. Yes. And Nicole. Yeah, let's do it now. It is fun. Ah,
I need to form a new subsequence with or can I just attach it over here? The answer to that is so let's attach it over here. Why? Because if you to 8, now if you're having 8, it's still greater than 7. So I've attached it. Next I go to 4. So I see I can either start with 4, but my brain says, but Striver, there is one which you can take at 5. Can I attach it here? The answer to that is no, Striver, you cannot. Can I attach it over here? Yes, Striver, you can. Perfect. Next I go to 6. I have a 6. Can I attach it over here? No. Can I attach it over here? Yes. Perfect. Next I go to -1. Where can I attach it? Now, my brain says, we can't attach it. We cannot attach a -1 here. We cannot attach a -1 here. But we can start fresh. Will -1 have anything before? No, it's the smallest. So I will have -1 right before this. Perfect. Next I go to 9. So when I go to 9, I can attach 9 here. I can attach 9 here. I can attach 9 here. So assuming I attach to everyone, assuming it's over. So once you end it, you see this is a length 4. You see this is a length 5. You see this is a length 2. And eventually, and you make new subsequences at every junction. Not move this way. But this is an intuition which helps us to think of binary search. So tell me one thing. Like I don't need to print LCS. I just need 5. I just need 5. So can I do something like this? When I was carrying 178 and this was done, when 4 came in, can I say 178? Let's rewrite 4 over here. Can I do something like this? Rewrite the same subsequence. Can I do something like this? And the answer to that is yes, Trigger. We can do it. And let me show you what I'm actually talking about. Because we're just concerned about the length. We're just concerned about the length. We are at 1. Let's have 1. We are at 7. Let's have 7. Something like this. Can I say 178? Let's rewrite 4 over here. Can I do something like this? Rewrite the same subsequence. Can I do something like this? And the answer to that is yes, Trigger. We can do it. And let me show you what I'm actually talking about. Because we're just concerned about the length. We're just concerned about the length. We are at 1. Let's have 1. We are at 7. Let's have 7. We are at 8. Let's have 8. We are at 4. Instead of making 1 4, since we are actually not concerned about the alias and we're concerned about the length, we will say where can 4 fit in the existing subsequence? I say 4 can fit in here. So what you do is, remember, what you do is you take the 7 out. You take the 7 out and you say 4 can fit in here. Remember this, that it does not mean 148 is a subsequence. No. I'm just making sure instead of storing 1 4 separately, I stored 1 4 right over there to save space. Even if someone like 9 comes in and because I know if 8 is there, why is 8 here? Because previously 7 was there. That's the reason 8 is here. That is something which we definitely know. So we are sure that before the 7, I overwrote the 7 to 4 because it's okay to overwrite because we're not concerned about the alias, we're concerned about the length. So I overwrote it at that place itself. Okay, let's move across to the next, which is 5. Okay, where can 5 be? I either go and create like 1 4 5, or I either say let's not create, and instead of that, let's omit 8 and write 5 because either you're carrying 178 or either you're carrying 1 4 5. It still makes the same. Right after this, amazing. The moment I have -1, where can I have it? Right over here. Replace it. So I replace it over here, saying not 1, it's going to be -1. Perfect. Where can I have 9? Will be your answer, which is 5. Because again, a very simple one. Because initially you had 1, then you had 7, then you had 8. The moment you got 4, you want to insert 4. If there is a 4, you insert it at that place. Or you say, hey, listen, there is no 4. So please go across and insert it right after 4. Right at the first element after 4. At the first element after 4. Can you please do it for me? Right at the first element after 4. So since you know this is sorted, in order to insert 4 here, you can simply do a binary search. And binary search will say 4 will go here. Next you go to 5. Binary search will say first element after 5, that's 8. Binary search will say I'll go here. 6. First element after 6, no one, so goes here. First element after -1, that's this. First element after 9, that's this. That's how you get the length. That's how you replicate. That's the first like 1 4. So you put it across 1, you get the like in this case, if you see when I inserted 4 8. So if you're doing a lower bound on any array, it gives you the first index, it gives you the index of array of I if exist, or gives you the first index which is greater than array of I. In order to understand it in depth, you can watch the video link in the description.
Cool. And IS is done. So how will LIS work? Let's go through it once more. Uh, I'll go through the array whenever I find, let's say I find a number that's greater than the top of the array, like the back of the array, I add pushback on that array. If I find a number that is smaller, then I find the lower bound of the number and replace the number. And at the end, I'll have the size. Coin change. Coin change. Um, amount. Amount will change. Mm, yeah. This is how we can do it. There's a one constant for amount. Basically, we are finding the minimum height of a tree in this, like the arm with the minimum height. And so we can do solve amount, uh, mm, so it's a kind of different ways on this number of times. We solve amount dot coins. Okay, now in solve. Okay, and, amount comma the coins. Now if amount is versus zero, then in that case return one. Okay, if amount smaller than zero, return zero. Okay, and okay, now for auto x of coins, what I do is um, min of A answer and solve of AMOU minus x comma points if answer especially in uh, um, cool. If amount is equals to 0. So let's do a dry run. Okay. So for exchange coins, we'll take 11 for one. Uh, let's see. If amount is equals to 0, then output should be 0. Yep. Mhm. No answer plus one. Okay, this will give TLE, but I have the answer. Let's memorize it. So amount is the only variable. So if it's a function of amount, and so memorization will be done according to that function. So um, so at max it could be amount. So n amount plus one. Of size. comma, okay, and pass v, v, pass v, and after passing v, and if v of amount um, is vector, what's vector? Vector, vector, comma v, okay. So we have done bottom up. Let's optimize this a bit. For I is equals to 0, I smaller than amount. When I is equals to amount, okay, 0. So Okay, so amount I redundant is equals to 0 I minus and the amount is 0 already. Now this so int answer is equals to int max. Okay. For x in coins, min of answer, comma, I is equals to 0. Let's start from 0. I smaller than amount I plus. Uh, uh, I minus x v of I minus x if I greater than is equals to x, okay, v of I is equals to into max v of I is equals to answer plus 1. I think this should work. If at the end of v of amount v of amount is as I is greater than 1. So for zero, the answer is zero. Yeah, and that's yes. Start by one. Uh, for zero, the answer should be zero. One, the answer is one. For two, the answer should be one. Huh? I equals. Got it. Submit. This is the. I don't think we can space optimize it because the points could be very random, and that's the reason. So we can't keep an integer or everything for a coin. We can, like, if we want, we can keep the. Let's say there are three coins. For this, we can keep like three variables, and for four, we can keep an array of four and keep that. But that does not make a lot of sense. Let's leave it. We have reached the I'm proud of us. I think this is good. Point change is done. Maximum product sub array. How many questions? I think I have reached 99. This will be the 100 question. So 4 days, 100, 25 per day. Good. More than 100, I think. I'll complete this in 5 days. If things, I don't think I'll complete this in 5 days, but yeah, 6 days mostly. So at this speed, I think these would take some more time with manipulation. Counting bits I can do right now. Uh, Even an integer and such that is. I can also use bit set for this, but instead of that, okay, counting bits is not what I. Counting bits in all numbers from 0 to 1, I guess. Question. Number of way of emphasize such that for each I, okay. So 0 has 1, 1 has 1, 2 has 1, 3 will have 2. So I think there would be a pattern, I guess. Yeah. So 0, 1, I think there would be a pattern. 0, 1, now 1, 0, 1, 1. Okay. So when we start 3, 1, 0, 0, 1, 0, 1, some pattern, I guess. Okay. What have I done? For n is equal to 0, return 0. For s equals to 1, return 0, 1. Vector intercept 0. We have 0 is equal to 0, we have 1 is equal to 0, I is equal to 2, I is smaller than n, and k is equal to I by 2, j is equal to I, p of I. Yeah, I think I remember sheet.google.com. So 1 has 1, so 0 has 1, 1 has 1, so 0 has 0, 2 has 1, 3 has 2, 4 has 1, 5 has 2, 6 has 2, 7 has 3, 8 has 1. Okay, so if we look at this 0, 1, 1, 2, 1, 2, 2, 3. So in the first one, it's 0. Then 0 and 1. Okay. That is how it starts, the series starts. Then next 1, 2. Okay. Which is plus one of these. Okay. Then next series 1, 2, 2, 3. Okay. So next series will be 1, 2, 2, 3. So 9 has 2, 10 has 2, 11 should has 3. Exactly. So this is every series has, let's say, series starting from, so 0 has 0, 1 has 1. Now series starting from 0, 2 has, uh, from this series. I take the series and I add 1. So 1, it will add, this will add 1, this will have. Okay. Now till the next numbers, I double this. Okay. So this is how I will construct. So 0, 1. Okay, this will be the original. After this, I'll just add 1 to this. 1, 2. Okay. Now for the next four, if the number is greater, then 1, 2, 2. Let's say we find a number, we stop. And if the number was, let's say, 0, 1, 2, 3, 4, 5, 6. If the number was 6, then we stop. If not, then we continue. So that's how I think it will be done. Let's see. Too much logic that I'm using here. I'll just store the size after 0, 1. Store the size, run I from that to that, and see if the size is equals to the n every time. And I think this is easy. If we want, like, my solution would not be as efficient. So it will be, uh, let's say I want to calculate for 10. So 0, 1 will be, so for that, 1, 2. Next to calculate, two raised to log 2, something like that. What will be my time complexity for that? Okay, so let's say I want to calculate for 10. Okay, so how will I do it? I'll have an array of 0, 1. So for the next number, I'll do two operations. So I'll have till 4. Let's say I have 0, 1. For till the next operation, I'll do 1, 2. So two operations. The next, I'll do 1, 2, 1, 2, 3, 4. So four operations, and we keep on increasing. So 2 plus 4. So it's a series. And if I want to do till 8, let's say, uh, so till 8, I will have to do this log base, log of n times. So the time complexity will become GP some formula from 2. Okay, yes. So 2 raised to log n. 2 raised to log n. So for 8, I will only have to do this 1, 2, 1, 2, 3, 4. For 16, let's say 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so n, it's a n operation, I think. Of n. What is the time complexity that I have with the solution I have written this? It should be also n. Yeah, it had the similar logic, but I've refined it. Let's go to editor. Popcorn. Solve the problem number of. Okay. How does popcorn work? Count is equals to 0, x not is equals to 0, plus plus count. Okay. Let's say I have 2. Okay. So count is equals to 0. 2 not is equals to 0, plus plus count. 2 and 1. So that will be, count will be 1 and it will go out. Okay. Cool. Now 3. Let's say 3. 3 and 2. What will 3 and 2 give me? Um, 1. Will it? No. 3 and 2 will give me 2, and 2 and will give me. Okay, cool. So I can do this. Suppose we have an integer. This is my solution, similar to mine. Let's just see a video on this. Though I have solved this, but I want to get better at this topic, I think.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to be solving a binary question, counting bits. And this is one of the binary questions from the blind 75 list that we changed to an easy problem for every integer in the range from 0 all the way up until and 2. And basically, what is the number of ones in the binary representation of this particular integer? Now, what's the binary representation of 0? It's of course just 0, right? As many as we want. Output is going to look like leading 0 is very the binary representation 1. So we have at least like what kind of operator to this integer is basically going to take that ones place and remove the division is going to get we're taking 1, this ones place now and chop it off. And now we're left with a single 0. So if you take 1 divided by 2, yes, you get 0. Once we get to 0, that's how you know when we're stopping, right? There's
मारने दो
obviously in
भाई
0, there's no more
मारने दो
ones in 0.
क्या ही कर लेंगे भाई मारने दो सबको फिर टेक डाउन कर लेंगे वीडियो कोई
So
नहीं
basically we counted two different ones. So that's how we would do it for every particular integer. The example I showed right now is 3. And to get this, the time complexity is log n. Because for any integer n, how many times can you divide it by 2? Well, of course, that's just log base 2n. Now, we don't really worry too much about the base usually, but yes, it's going to be log n, log base 2n. That's how many times we could divide any particular integer n by 2. And of course, we know we're doing this for a bunch of integers in the range all the way from 0 to n. So we're doing this n times. Doing a log n operation n times is going to be time complexity n log n. Now, there's some repeated work that we can eliminate that you can easily recognize when you actually draw out the bit mappings, the binary representations of a bunch of integers. And with that repeated work, we can actually get a working O of n solution. Let me show you that right now. Now, I just drew out the binary representations from 0 all the way up to 8. So we notice how we have a 1 and eighths of the previous 2 over here. We were just adding 4 to it. So extra 1 in this position, right? Because we just got this one. This one represents a 4. This is there and count how many ones were, how many bits, how many ones were in position. In other words, this is going to be 1 plus dp of, because that's what's going to match up with this, which is going to tell us how many ones are going to go here, right? So clearly we see that that's a 1. So here we're going to compute 1 plus, again, dp of n minus 4. And similarly for here, so in this position, really there's going to be 2, 1 is offset by 4. So this is going to be 1 plus 2, since the integer occurrence of 1. And then we want 4, because if we do an offset of n minus 8, you can tell that for each value, this is going to be the 06 is going to be this up just a tiny bit. So we know that this is kind of our base case. 0 is going to have 0. We're going to compute 1 plus dp of n. N is always going to be the value we're computing right now. So that's going to be a 1 minus 1, because 1 is the most significant bit we've reached so far. Down here, we reached a new significant bit of 2, right? Because we've gotten to the value 2, it's about power of 2. So then we're going to be modifying this n. Let's say we multiply it. We did 4, 8, this zeros, and it's going to be at least 1 plus dp of
आंसर तो मजा तो आता है मजा आता है counting bits than string number. Given a non-empty array integer, every element appears twice except one. Find the singles. We'll just draw. So if these appear twice, they'll all get reduced and like they'll not show up in the answer. So yeah, simple. So what was single number? Yeah, reverse bits. So I think I should explain it better. Like if these number so 2 XOR 2 will become 0 because all the XOR is an even odd calculator and odd bits of 1. So in that it will have only even numbers and so it will get reduced to 0 and so at last 1 will be left. Reverse bits of a given 32-bit unsigned integer. No, that's all my answer, Joel. I have no unsigned integer power in that game. I'm not sure how we'll do this. Because I don't understand this type only. What is this type? The so if I have, let's say, A, A is equals to 4, what will I return? Okay, so I'll just have to return the number, I guess. For the number, I can also do this uh, bit set of n dot. I need to learn bit set operations because this will be very useful for bit validation. Set reset with count. None. Can I do this? Um, okay, first thing, bit set of 32 bytes bits and B of n. Cool. We declare a bit set. Now reverse D dot begin, comma E dot end. D dot begin and D dot end. B. Can I do this? B E G N. Two string to straw or size. What all can I do with a bit set? Bit set. Any or none test. What does test do? Set, all set, reset. Can I do like this for bit set? C out B of 0. I think I can do this. If that is the case, then mm, okay, I think I can do this with bit set. So I just go, I should do this. I is equals to 0, I is smaller than 16, I plus plus, and what should I do for each number? Swap b of I, comma b of I 32 minus I minus 1 minus 1. Um, mm, return 150 of 2 u long of b should work. Bool b is also b of I, b of I dot is equals to